Put this star where the sun is, Saturn disappears inside. It's called Stephenson 218, the current size champion by radius. Immediate takeaway, we finally have strong numbers to back it. The surface would glow cool red like dim embers in fog. Largest here means biggest radius, not mass or brightness. That detail matters because stars grow puffy as they age. Astronomers pinned its distance, then derived its size from temperature. So the claim is not hype, it's math with error bars. Example, in real terms, the radius spans roughly 10 astronomical units. That reaches beyond Saturn's path, brushing the space near Uranus. So the picture is a red world swallower anchored in a cluster. Step back to the crowded heart side of our Milky Way. Dusty lanes cross a busy spiral arm, stars packed tight and warm. In that tangle sits the Stephenson 2 cluster, glinting through haze. One member burns huge and gentle red, swelling against the dark. A red supergiant is a massive star with a bloated envelope. It looks cool and dim per square meter, yet blinding overall. This matters because these giants forge and spread the heavy elements. They feed future planets and they set the stage for supernovae. They also preview our sun's distant fate, though not this extreme. Here is how a star gets that big in brief. The core runs out of hydrogen and contracts under gravity. Outer layers respond by expanding, cooling, and becoming loosely bound. Enormous convection cells rise and sink, dragging molecules and dust. Pulsations make the atmosphere breathe, like a sleeping bellows. Example, in real terms, think continents sized like orbits on the surface. Each bright cell can span Mars to Jupiter in width. Now put a label on our target stats cautiously. Its surface sits near 3,200 Kelvin, pleasantly tepid for stars. Its light equals roughly 500,000 suns, flooding the cluster. That power at that temperature implies an outsized radius. Numbers put it near 2,150 solar radii. Place it here and Jupiter's sky would be inside the photosphere. Bottom line, a red supergiant is a cool, bright, swollen powerhouse. Claims this bold live or die on distance. Parallax gives that distance, using Earth's orbit as a measuring stick. Gaia watches stars wobble slightly because perspective shifts across the year. Tiny angles, precise timing, and relentless repetition build clean numbers. That is crucial because size depends on two linked quantities. You need how bright it truly is, not just appears. And you need its surface temperature set by the spectrum. Once you have luminosity and temperature, radius drops out neatly. We use the Stefan-Boltzmann relation, which ties heat to area. Example, in real terms, double the temperature and brightness soars. Brightness scales with temperature to the fourth power dramatically, so a cool star must be vast to shine that much. Data from Gaia DR3 anchors the cluster around 19,000 light-years. Spectra put Stephenson 218 near Type M, very cool and red. Its temperature sits near 3,200 Kelvin, give or take. Its luminosity lands near 500,000 suns, within uncertainties. Rule of thumb, big luminosity plus low temperature means a huge area. Crunching those inputs yields a radius near 10 astronomical units. That means the photosphere would reach beyond Saturn comfortably. Include realistic error bars and it still dwarfs almost every rival. Past champions lost ground when distances shifted or dust fooled photometry. This one sits in a cluster, so the distance holds steady. Net result, the radius claim rests on geometry, physics, and cross-checks. Now zoom to the star's seething skin, mottled like boiling lava. Bright upwellings rise slowly, then fade as they cool and sink. The air here is thin, dusty, and barely held by gravity. A stellar wind slips away constantly, carrying gas into surrounding space. Mass loss is the quiet leak that reshapes a giant's life. It decides how much fuel remains and when collapse begins. It also seeds the neighborhood with molecules, dust, and future rock. How does that leak actually start up close? Pulsations push the outer layers outward, easing the grip. Dust condenses in the chill, a few stellar radii out. Starlight pushes on that dust, and the dust drags the gas. Convection and shocks kick clumps free, like gusts lifting ash. The flow turns into plumes and arcs, not a smooth breeze. Example, in real terms, imagine several Earths of mass each year. Rates can reach a millionth to a 10,000th of a sun yearly. That is enough to build rings, shells, and comet-like knots. Radio and infrared maps often show arc after arc expanding. These structures record years of breathing, like tree rings in smoke. As the envelope thins, the photosphere swells and shivers even more. The star brightens, dims, and sheds yet another veil of dust. Bottom line, a giant this loose peels itself, layer by layer. Those peeling layers create a magician's smoke that tricks our eyes. Around a red supergiant, dust glows warmly in the infrared. It absorbs blue light and it re-emits redder light later. That shift makes the star look brighter at longer wavelengths. It can also look physically larger because halos blur edges. Interferometers try to resolve the true photosphere through that haze. They mix light from separated telescopes to sharpen the picture. Common mistake is treating the halo as the star itself. Past records fell this way as models improved and distances changed. UI Scuti once topped lists, then its radius was revised downward. Better distances shrank it, and dust around it fooled estimates. Other icons took similar hits after new parallax arrived. This matters because record claims invite bias and dust bites hard, so astronomers lean on multiple methods and on clusters for context. They fit spectra, map halos, and compare to theoretical tracks. Example in real terms, knock 10% off distance, size plunges. Distance error appears squared inside luminosity, compounding fast. Dust can skew temperature, which also hits radius as fourth power. Two small misses can balloon into a huge, wrong radius. Stephenson 218 survives these traps better, thanks to its cluster. So the picture is a cleaned measurement, not a mirage of smoke. Pan wider again to the hive of siblings around our giant. A cluster is a family born together from one cloud. Members share an age, a distance, and a motion through space. That unity lets astronomers compare apples with apples confidently. You can plot brightness versus color and trace a curve. That curve, an isochrone, tells the family's shared age convincingly. Once you know the age, masses click into better focus. Massive stars peel off the curve first, leaving telltale gaps. Mass decides the ending in stellar lives. For Stephenson 218, the family points to a young age. Think around 15 to 20 million years, with dusty veils complicating. Such youth means it began heavy, likely dozens of suns. Many analyses land near 40 solar masses at birth, roughly. Since then, winds probably shaved several suns of mass away. The envelope puffed as burning moved to shells around the core. The core, meanwhile, grows heavier, denser, and closer to collapse. Example in real terms, the core could pack several suns inside Earth size. Outside, the photosphere still lounges near 10 astronomical units in radius. That split personality drives the instability and the prodigious wind. When the clock runs out, a dramatic stellar death likely follows. Net result, the cluster's shared story locks the star's scale in place. How big can a star get before it tears itself apart? There is a balancing point called the Eddington limit, simply put. Gravity pulls inward, while radiation pushes outward on particles and dust. When push nearly matches pull, the envelope balloons and turns unstable. That ceiling matters because it explains why sizes rarely exceed certain numbers. Here is the practical picture, skipping equations but keeping meaning. Cool surfaces reduce radiation pressure at the edge slightly, but the luminosity is enormous, so the push is still fierce. If you add more puff, the outer layers decouple and fly. Winds ramp up, clumps detach, and the star sheds faster. The system self-regulates, grow bigger, lose mass even quicker. Rule of thumb, near 500,000 suns of light at 3000 Kelvin, you get about 10 astronomical units. Go brighter at the same temperature and the wind explodes. Go cooler at the same luminosity and dust grabs more push. Either route limits the maximum radius, on average over time. Example in real terms, models overshoot briefly, then peel back quickly. Observations catch those overshoots as arcs and fresh dust plumes, so the giant hovers around that 10-unit scale, season by season. Bottom line, physics sets a size ceiling, not just lucky coincidence. Circle back to the image from the opening moment. Place the star at our sun's address and Saturn is gone. Yes, that claim stands, with numbers anchored by Gaia and physics. We met a red supergiant, swollen by shell burning and winds. We saw how distance, temperature, and luminosity map to radius. We watched dust play tricks and how clusters steady the picture. We traced a ceiling set by radiation pressure and gravity. So the largest known by radius today is Stephenson 218. It may change with new data, but the method endures. If this kind of clear space sleuthing hits your brain just right, stick around. I post deep dives with crisp visuals and zero fluff. Bottom line, Saturn would sit inside and the math makes it real.